The title of the paper is Confident Monte Carlo, Rigorous Analysis of Guessing Curves for Probabilistic Password Models. Our speaker for this paper is Jeremiah Blocki from Purdue, and he's a faculty member at Purdue. So let's give a warm welcome to Jeremiah.
All right, thanks for the introduction. So I'm excited to tell you about our paper, Confident Monte Carlo. This is joint work with Peiyuan and Wenjie, my PhD students. All right, so let's just return to two fundamental questions in password security. Strength estimation, we're given a password, and we want to know how many guesses will it take an attacker to crack my password. So unlike the previous talk, in this talk we're going to assume that the attacker uses some state-of-the-art model M. Another task we might be interested in is estimating the guessing curve, right? So what percentage of passwords will be cracked within B guesses? B could range from small to large depending on whether we are dealing with an online or offline attacker. Okay, so a naive solution to answer these questions is to just brute force enumerate all of the guesses that the model is going to generate. Unfortunately, this can be cost prohibitive. So in 2015, there was an efficient technique called Monte Carlo strength estimation, which yields an unbiased estimate of the guessing number. So this has become a very popular tool in password research literature because it allows you to efficiently compute the guessing number or guessing curve. Unfortunately, one of the things we'll point out in this paper is that unbiased estimate does not necessarily mean accurate with high probability. So our first contribution is to provide theoretical examples of probabilistic password models and problematic distributions for Monte Carlo. Right, so we'll give an example where Monte Carlo generates highly inaccurate guessing numbers with high probability or highly inaccurate guessing curves with high probability. Okay, so given that there are problematic examples out there, we'd like to avoid just confidently reporting a guessing number or guessing curve that's not accurate. So our key contribution is to introduce a new tool called Confident Monte Carlo. Basically, in a nutshell, we're extending the Monte Carlo tool with confidence intervals using rigorous statistical techniques to upper and lower bound the guessing number or the entire guessing curve with high probability. So the guarantees are going to hold with high probability. And if we get a tight confidence interval, that means that we can be certain that our approximation is accurate. If we get a wide confidence interval, we can't know for certain that our approximation is accurate, but at least we know that our approximation is uncertain, and that's actually very useful information to know. Empirical analysis will show that the upper and lower bounds are typically very close. Okay, so let's dive in. What is a probabilistic password cracking model? So there's a number of examples out there, probabilistic context-free grammars, Markov models, neural network models, etc. Abstracting away, all of these models support two basic operations, right? They define a distribution, and I can sample from this distribution, or given a particular password, I can get the probability with which that password would be sampled. Right, so the model implicitly defines a distribution over passwords, and we have this sampling procedure. Now, an attacker using this model is going to order guesses by probability according to the model. And what we'd like to do is we'd like to compute the guessing number, right? So given a password, we'd like to estimate the number of passwords that the attacker is going to check before this particular password, right? Assuming that the attacker guesses in order of probability. Now, there are a few edge cases, right? What if multiple passwords have the same probability according to the model? For this talk, we're going to ignore that. See the paper if you want to handle those edge cases. The other note here is that we can define the guessing number for a password. Also, given a probability value, we can just define the guessing number for that probability value to be the number of passwords whose probability is larger than that probability value. Okay, so now a guessing curve is just the total fraction of passwords in a data set whose guessing number is smaller than a particular budget. Right, and we might be interested in plotting this guessing curve as the budget varies from small to large. Or, we might be given a password distribution, and we might be interested in knowing what's the probability a random password sampled from this distribution will be cracked within B guesses. Okay, so these are related questions we're interested in. All right, now of course the main challenge is how to actually compute these guessing numbers without brute force. Delamico and Filipponi had this clever randomized approach. Basically, their solution was to say, okay, well, let's sample a password from the model. Let's compute its probability, and let's define this random variable, which is just 1 over the probability if this password would be checked first and 0 otherwise. Okay, it's a simple estimate, and what they were able to prove is that in expectation, this is unbiased, right? So the expected value of this estimate is actually equal to the actual guessing number. Now, of course, this estimate has high variance, so what do? You reduce variance by repeating this process k times. Okay, so one of the things they can prove is that the variance converges to 0 as the number of samples approaches infinity. But of course, the whole point is efficient strength estimation, so in practice, k is bounded, which means that variance isn't necessarily converging to 0. And the question, again, is how can we be sure that this estimate is actually approximately equal to the real value? Okay, so we can actually define a problematic example of a password model. So again, this is a hypothetical example. I'm not claiming that real password models look like this, but right, imagine I have a model where password 1 is generated with probability 1/2, 2 is generated with probability 1/4, and so on and so forth. So the actual guessing number for password j is just j. Okay, and now if I draw a bunch of samples from this model, if I draw fewer than 2 to the I samples, then with high probability, all of my samples are going to be in this green set. I'm not even going to look at passwords beyond this green set. And one of the first effects that we observed was that we encounter a ceiling effect, where for all passwords, password j with j greater than I, their estimated guessing number is actually identical, right? It doesn't matter whether it's j equals I plus 1 or j is equal to 3i. They're going to get the same guessing number. Obviously, in reality, their guessing numbers can be very different. We can even push this example further, right? And we can take some of these less likely passwords and just replace I of these passwords with an exponentially large set of passwords. This has the effect of dramatically increasing the guessing numbers for certain passwords. But at the same time, Monte Carlo can't even distinguish between these two models, right? M and M prime are indistinguishable because with high probability, we're only going to sample from the green set. Okay. So now we can push this example even further, and we'll define a distribution which is uniform over these passwords 2i plus 1 to 3i. And if we set the guessing budget equal to 3i, well, under model M, the attacker is going to crack 100% of passwords. And under model M prime, the attacker is going to crack 0 passwords. Now, unfortunately, Monte Carlo can't even distinguish between models M and M prime, so it's going to have to give a highly inaccurate estimate for at least one of these two models. And this limitation actually turns out to be inherent to any black box tool for strength estimation. Now, confident Monte Carlo, our tool, is also black box. So does the limitation apply to our tool? Well, yes, it does. In this case, we won't be able to find tight bounds on the guessing curve. But what we will be able to find is that our upper and lower bounds diverge, and that will tell us that we're highly uncertain about the actual guessing curve. And this is, again, very valuable information. OK, so our work, Confident Monte Carlo, we introduced several rigorous statistical techniques to upper and lower bound the guessing number, and to upper and lower bound the entire guessing curve with high probability. So one of the results that we're able to show is that the Monte Carlo estimate, if you look at the difference between the Monte Carlo estimate and the real guessing number, it's upper bounded by order 1 over q times square root k, where k is the number of samples that we take. Proof sketch, we're applying Hofting's inequality, and this gives us an upper and a lower bound on the guessing curve, which applies with high probability. We can derive another lower bound using Markov's inequality and concentration inequalities. Basic idea is to do n different Monte Carlo estimates and take the median, and we can show that this yields a high confidence lower bound. Okay, skipping the technical details. Then, once we find a way to bound the guessing number, we can also extend this to upper and lower bound the entire guessing curve. The basic observation is, if we have an upper and lower bound on the actual guessing number, then we can upper and lower bound the actual guessing curve at that particular point. Again, see the paper for more details. Okay, so we did some empirical analysis using our tool. We considered several password cracking models, PCFG, 4-gram Markov models, transformer neural networks, and several different password data sets. I only have time to show you one or two of those experiments. Here we're looking at the upper and lower bounds for 3 models. And you can see the upper and lower bounds are actually fairly close, even as the guessing budget ranges from very small to very large. We're getting fairly tight upper and lower bounds, which is good, which means we're actually confident what the guessing curve looks like in this example. We might also look at how this compares to just vanilla Monte Carlo estimation. And we can see that most of the time, the Monte Carlo estimated curve lies in between our upper and lower bounds, so that's a good sign. There is one exception here. If you look at the yellow curve, you'll see that as the guessing budget gets too large, the yellow curve all of a sudden spikes up to 100%. This is due to a ceiling effect, and it's just a limitation of Monte Carlo. And our tools at least allow you to detect this ceiling effect. Okay, good. So we can also apply our tools to do hypothesis testing. In many applications, if you're conducting a user study, the number of samples in your data set is going to be small just due to research budgets. So we can apply our techniques in this setting. Again, see the paper for more details. Okay, so yeah, I'm over time, but thanks for listening, and I'm happy to take any questions.
Questions?
Great talk. What was this technique entirely invented by your group, or was there a previous work that used something similar and you built on?
So the question is whether this this technique was entirely invented by our group. Monte Carlo was not invented by us, right? That's prior work. I guess the statistical tools that were used, we're not going to claim to have invented them. To the best of our knowledge, we're the first to apply it to this particular problem. So yeah, I guess first to apply the statistical tools to this problem to the best of our knowledge.
Other questions? One question, Jeremiah. You showed some results on the upper and lower bounds for different models. Can you maybe comment a little bit on the upper and lower bounds for maybe different password data sets, and is there a correlation between the type of data set, maybe the size and your upper and lower bounds?
Yeah, so unlike the previous work, actually, we don't need to have super large data sets to get tight upper and lower bounds here. The reason is because the limiting factor is the number of samples from the model, not the number of samples from our data set. So that's one of the advantages of this approach, is you can get tight upper and lower bounds even when the data set is small. Now you do see different performance for different models and different password data sets. Some data sets represent either more security conscious users. So yeah, the guessing curves do vary a little bit from data set to data set, but they have the similar type of shape. we tend to see probabilistic context-free grammars. They tend to perform well when the guessing number is pretty small, and then neural networks tend to dominate when the guessing number is larger.
Thank you. All right, if there are no more questions, let's give a round of applause to Jeremiah. Thank you very much.